Tonight, we turn toward a strange and almost silent truth about a part of space that humanity has barely explored. The direction straight above and straight below the broad, flat plane followed by nearly all the planets. In the kind of cosmic view, Carl Sagan often invited people to imagine our solar system is not simply a collection of worlds spread in every direction. It is more like a thin arrangement of moving bodies, all traveling around the sun within roughly the same level path. Yet, among all the pictures humanity has taken of planets, moons, comets, stars, and distant galaxies, one important image is still missing. We have never taken a true photograph of our entire solar system from far above its main plane, looking down on it as a complete system. The problem is not that the destination is too far away, and it is not because engineers lack the desire to attempt the journey. The real difficulty comes from motion. Every spacecraft launched from Earth begins by carrying Earth's powerful sideways speed around the Sunday, escaping that shared orbital direction and climbing far above the planetary plane can require more effort than sending a probe all the way to Pluto. Over the next 2 hours, we will explore why this simple-looking journey is so difficult, what a spacecraft might discover if it ever reaches that high and lonely viewpoint, and how a surprising maneuver involving a deep fall toward the sun may finally provide a way to get there. If these journeys through space feel worth your time, leaving a like or subscribing can help the channel find other people who may enjoy them too. Thank you for spending this time here. But for the next 2 hours, you do not need to hold on to anything from the day behind you. Get comfortable. Allow the tension in your shoulders to ease. Let each breath become slower and quieter. Give the noise of the day permission to disappear. Let's begin. There is one simple but quiet truth about the place we call home that very few people are ever told in a direct way. Even so, it shapes every picture of the heavens humanity has ever captured. Our solar system is not a giant sphere filled with orbits, nor is it a scattered cloud of objects drifting in every direction. It is a disk, broad, slowly rotating, and almost as thin as a sheet of paper compared with its width. The planets, moons, asteroids and comets all move within this shared plane, circling the same central star, carried by the same steady sideways motion that has guided them for 4.5 billion years. The sun rests at the quiet center of that disk. The planets trace paths around it like markers placed along its broad rings. The direction that stands at a right angle to this disk, the one we casually call up or down, depending on which side we imagine ourselves on, is a direction that almost nothing in our everyday experience has ever traveled. The flat shape of the solar system is the most important geometric feature of our cosmic neighborhood. It is also one of the easiest to overlook because nearly every illustration of the planets is either shown from the side where the flatness seems ordinary, or from above where the disk is treated as something completely normal instead of being recognized as a remarkable structure in its own right. From Earth's surface, that disk surrounds us. The sun rises and sets along its path. The moon follows nearly the same route. The planets wander across that same track. Every familiar wandering light in the night sky, apart from the distant background stars, moves along one broad arc overhead known as the ecliptic. The ecliptic is simply the solar system's disk viewed from within, appearing as the path where nearly everything we know how to locate in the solar system can be found. This flatness is neither an accident nor the result of careful design. It is the lasting imprint of the way the solar system first came into existence. The explanation is one of the most peaceful and satisfying ideas in modern astronomy, and it deserves to unfold slowly. Picture an enormous cloud of gas and dust, far larger than any solar system, drifting quietly through interstellar space. Gravity pulls everything inward. As the cloud shrinks, its rotation is preserved, causing the spinning motion to become stronger in the direction perpendicular to the spin axis. The cloud is free to collapse along its spin axis because nothing resists that motion. Across the spin axis, however, it cannot keep collapsing unless it first loses the rotational motion supporting it. Given enough time, the shrinking cloud becomes flatter and flatter. The distance from pole to pole continues to decrease while the distance around its middle remains much larger. What once looked like a cloud gradually transforms into a disk. A young sun forms at the center of this disk, collecting most of the available material into one hot, bright core. Around it, the remaining disk cools, allowing heavier elements to condense into tiny solid particles. Those particles stick together. As they orbit, the growing clumps gather even more material. Planets slowly build up within the plane of the disk, naturally inheriting its flat structure. Anything that drifts too far above or below that plane is either drawn back toward it by the gravity of the disk, thrown outward and eventually lost, or never manages to come together in the first place. Once the original cloud acquires angular momentum, that motion becomes the steady sideways movement that keeps the disk spread across light hours of space. The original disk in which the planets formed has long since disappeared, blown away by the intense light of the young Sunday. Even so, the planets remain close to the plane that ancient disk established. The same pattern appears everywhere in the universe, whenever gravity and rotation work together. Saturn's rings form a small disk. The Milky Way is an enormous galactic disk. The accretion disks feeding black holes are also disks, shaped by the same physical rules. They rotate, contract, flatten, support themselves outward through angular momentum, and continue collapsing freely along their poles. When gravity and rotation act together, flatness is usually the natural result. A perfectly spherical solar system would actually be the unusual case. A disk is what nature most often creates. The plane into which our solar system settled has a specific name. It is known as the invariable plane, defined as the average of all planetary orbits, weighted according to their angular momentum. The planet contributing the greatest share of angular momentum has the strongest influence on this average, which is why Jupiter, being the most massive planet, pulls the invariable plane strongly toward the orientation of its own orbit. Earth's orbit, the one every listener is traveling along at this very moment, is tilted by only about 1.5 degrees Celsius compared with the invariable plane. In practical terms, that difference is so small that astronomers usually treat the ecliptic, the plane of Earth's orbit projected across the sky, as though it were the plane of the solar system itself. Nearly all of the major objects in the solar system orbit within just a few degrees of the ecliptic. Mercury, the closest planet to the Sun, has an orbital tilt of about 7 degrees. Venus, Mars, and the giant gas planets have orbital inclinations that are only slightly larger. Pluto, the best-known exception, travels at an inclination of about 17 degrees, giving its path a clear rise above and dip below the main planetary plane. A small number of icy objects located well beyond Neptune follow even steeper paths, while some long-period comets approach from almost every possible direction, cutting through the disk before disappearing back into deep space. Even so, these are only small exceptions within an overwhelmingly flat system. Most objects orbiting the Sun remain confined to a narrow, flattened region of space. The disk itself did not vanish once the planets finished forming. A thin veil of tiny dust particles still remains along that same plane, slowly renewed by the normal activity taking place throughout the solar system. Collisions between asteroids occurring constantly and quietly in the region between Mars and Jupiter break larger rocks into smaller ones, then into even finer pieces. until they become microscopic dust grains. Comets passing close to the Sun leave trails of dust scattered along their orbits, even those originating far beyond Neptune. The gradual wearing away of distant icy bodies also supplies a faint amount of material from the outermost parts of the solar system. Nearly all of this dust stays concentrated within the same plane because the objects producing it orbit there, while solar radiation pressure, together with the gravitational pull of the planets, helps maintain its overall distribution. The outcome is a thin, dimly glowing disk of dust that continues to outline the structure of the solar system long after the original protoplanetary disk disappeared. Under exceptionally dark skies, far from artificial lighting, this dust can actually be seen without any telescope. It appears as a gentle cone of pale light stretching along the ecliptic, rising from the horizon shortly after sunset or reaching upward before sunrise. This phenomenon is known as the zodiacal light, named after the zodiac constellations that lie along the ecliptic. The zodiacal light is simply sunlight reflected and scattered by the dust spread throughout the planetary plane back toward Earth. It is not an atmospheric glow, nor is it an aurora. It is the solar system's own dusty disk, made faintly visible as sunlight bounces off countless tiny particles. Seeing it with the naked eye means directly seeing the shape of the place we call home. The zodiacal cloud is thickest close to the sun and gradually becomes thinner farther away. It also rapidly decreases in density above and below the planetary plane. A somewhat brighter feature, commonly called the asteroid belt dust band, marks the dust created by collisions within the main asteroid belt between Mars and Jupiter. Even farther out, beyond Neptune, a much fainter contribution comes from the slow erosion of icy bodies over immense periods of time. Viewed from within the solar system, the disk appears as a soft ribbon of light crossing one part of the sky. Seen from above, it would resemble a broad, flat sheet of dust, with the planets moving through it like beads sliding along invisible tracks. The inner regions would shine more brightly, while the outer portions would gradually fade into the darkness of space. The arrangement of this dust helps explain why the solar system's vertical direction is so unusual. Looking outward along the plane means looking through larger amounts of dust, more sunlight scattered by that dust, and more of the solar system's own background glow. Looking straight above or below the plane is completely different because there is very little dust in those directions. The regions directly above the sun's north pole and directly below its south pole provide some of the clearest possible views of the distant universe from anywhere inside our solar system. The very disk that forms our cosmic neighborhood is also what fills much of our view. Looking away from it offers the least obstructed window into the wider universe. You may already understand the ecliptic without ever having learned its name. If you have watched Venus shining low in the western sky after sunset, noticed Jupiter following the same curved path, and then seen the moon travel along that identical route several nights later, you were already following the ecliptic with your own eyes. The planets never move randomly across the sky. They stay close to one continuous path because they all orbit within the same shared plane, a plane inherited from the disk where they first formed. What we see from Earth is simply that disk viewed edge-on. Astronomers rely on two primary coordinate systems to describe locations across the sky, and both are based on the structure of our local surroundings. One system uses the celestial equator, which is Earth's equator projected outward into space as its reference plane. The other is based on the ecliptic itself. These two planes are inclined relative to each other by about 23½ degrees, exactly the same tilt responsible for Earth's changing seasons. Earth's axis of rotation is not perfectly perpendicular to the plane of its orbit, and because of this tilt, the celestial equator and the ecliptic intersect at two special points known as the equinoxes. For tonight's journey, All the listener really needs to picture is one simple idea. The solar system has a natural flat plane. The planets all travel within it, and the directions above and below that plane are places that almost nothing we have ever sent into space has traveled. That flat disk of the solar system also exists inside something much larger, the immense disk of the Milky Way galaxy. The Milky Way is a slowly rotating spiral stretching across hundreds of thousands of light years, containing several 100 billion stars, along with enormous amounts of gas, dust, and dark matter. Just like the solar system, its disk formed because rotation gradually flattened it over immense stretches of time during its creation. Even so, the galactic disk is not aligned with the planetary disk. Instead, the two planes are tilted relative to one another by about 60 degrees. The Sun and all of its planets circle the center of the galaxy within their own separate plane, one that points in a noticeably different direction from the galaxy's main disk. Living inside the solar system, we hardly notice this difference, yet it becomes very important when we ask what someone would see from high above the Sunday scene from Earth. The glowing band of the Milky Way stretches across the night sky like a broad horizontal path. The bright central bulge of the galaxy, easiest to observe from southern latitudes during certain times of the year, marks the direction of the galactic center. But if an observer were floating above the Sun's north pole, that familiar band would appear sharply tilted instead. The glowing center of the galaxy would occupy a completely different position compared with the ecliptic. The southern constellations, the dark ribbons of dust winding through the Milky Way, and the gentle light coming from the galaxy's crowded central regions would all remain present, yet their arrangement would be noticeably different from the one we know on Earth. The stars would not change. It would still be the very same sky. Only its orientation would feel unfamiliar in a way that is difficult to picture until someone views it from a place unlike any they have ever experienced before. The Sun, you're also traveling through the Milky Way mirrors. When that motion is projected onto the background of the sky, it points toward an area within the constellation of Hercules. Throughout the entire lifetime of the solar system, the Sun has carried every one of its planets along during this slow journey, passing through an enormous region of the galaxy as it continues its orbit around the galactic center. Inside a broad, somewhat stretched bubble created long ago by ancient supernova explosions lies a region of thin interstellar gas known as the local bubble. This bubble is not evenly shaped. One side opens more freely toward the wider galaxy, while the opposite side is more confined. Looking below the Sun's south pole in terms of the galaxy leads into one of the clearer viewing directions through this region. The plane of the planets, the plane of the galaxy, and the direction standing at right angles to both all cross the same part of the sky we observe every night. We exist where several different disks, several different layers of flatness, and several long-established rotations all come together. Our position is not random. It is the outcome of giant clouds collapsing, gravity bringing order, rotation flattening matter, and time slowly shaping everything into its present form. The single most important truth about the solar system, the one that allows everything else in tonight's discussion to fit together, is that it is flat. The disk is real. The vertical direction is real. Everything that follows is simply a calm exploration of how rarely humanity has ever looked along that vertical path and what might appear if we finally did. The most important reality about leaving Earth is something that is seldom explained outside the rooms where space missions are designed. Yet it controls nearly every movement a spacecraft makes once it enters the solar system. None of us are standing still. The ground beneath the listener is constantly moving, not because of earthquakes or any local motion, but because the entire Earth is racing sideways around the Sun at a speed so smooth and steady that we never notice it. Earth's orbital velocity is roughly 30 kilometers per second. Every single second, our planet moves another 30 kilometers along its path around the Sun. Every minute it covers 1,800 kilometers. Every hour it travels more than 100,000. The listener, the room around them, the building, the atmosphere, the oceans, the solid crust, the molten core, and the entire planet all share that same tremendous sideways motion together. The instant a rocket rises from Earth's surface, it already carries all of that sideways speed with it. It does not have to build up its orbital velocity around the Sun from nothing. Simply by sitting on a launch pad on Earth before liftoff, it already possesses 30 kilometers per second of sideways motion around the Sun. To enter orbit around Earth, a spacecraft must gain the extra speed needed to remain in orbit around our planet, which is about 8 kilometers per second relative to Earth's surface. After that, the additional speed required to break free from Earth and head toward the Moon, Mars, or Jupiter is much smaller because the Sun's gravity already governs the overall path of those voyages. Rather than creating an entirely new journey, the rocket simply adjusts the orbit it inherited into a different one. At no point does it remove the sideways motion around the Sun that it received from Earth. It never becomes stationary relative to the Sun again. This inherited motion explains why nearly every spacecraft ever launched has traveled more or less within the same flat plane as the planets, and why almost none have ventured far above or below that plane in any significant way. To leave the ecliptic, a spacecraft cannot merely travel upward. It must first overcome the 30 kilometers per second sideways velocity it inherited, and then replace that motion with the same amount of speed directed elsewhere. That new direction must point above and away from the planetary plane. The ecliptic is not like a highway. It behaves more like a powerful current. Everything inside it is carried along together, and changing direction is vastly more demanding than continuing with the flow. Engineers have a name for the total amount of velocity change a spacecraft can achieve using the fuel it carries. They call this delta V, the total change in velocity the vehicle is capable of producing. Delta V serves as the true currency of travel throughout the solar system. Every maneuver spends part of that supply. And once the available delta V has been exhausted, the spacecraft cannot perform additional major maneuvers. The size of this reserve depends on the amount of fuel loaded at launch and on the efficiency of the propulsion system. Chemical rockets, the same type that have launched spacecraft from Earth and have been improved through about 70 years of practical engineering, and have performance limits that place realistic boundaries on the total delta V they can provide. The figures that follow are approximate, but they are accurate enough for our discussion tonight. Reaching low Earth orbit from Earth's surface requires about 9 to 10 kilometers S of delta V. Most of that is spent overcoming gravity, pushing through atmospheric drag during ascent, and building the sideways speed needed to remain in orbit after leaving the atmosphere. Escaping Earth orbit on the way to the Moon requires an additional 3 or 4 kilometers per second. Traveling to Mars along the standard low-energy transfer path during a favorable launch window when the planets are properly aligned requires roughly 4 kilometers per second of delta V beyond Earth orbit. Reaching Jupiter, whether gravity assists are used or not, typically demands about 6½ k-meters beyond Earth orbit. These destinations are the familiar goals of planetary exploration, and the required delta V remains well within the abilities of modern launch systems, provided the spacecraft stays within practical size limits and the mission is designed with care. A mission that truly departs from the flat plane of the solar system, climbing straight above the ecliptic into the open space above or below it, faces a completely different challenge. Such a journey requires removing nearly all of Earth's sideways orbital velocity and replacing it with an equally large velocity directed at a right angle to the planetary plane. The required cost is around 30 kilometers per second of delta V starting from low Earth orbit. No chemical rocket has ever supplied that much delta V to a single spacecraft. Even the most ambitious interplanetary missions in history have carried total lifetime delta V budgets of only about 15 to 20 kilometers per second. Most of that capability has been spent slowing down to enter orbits around another world or making trajectory corrections after arrival. A direct climb out of the planetary plane is not just somewhat beyond our reach, it remains far beyond what chemical rockets can accomplish. Pause for a moment and think about how surprising these numbers really are. Sending a spacecraft all the way to Pluto near the outer boundary of the planetary system requires less delta V than sending that same spacecraft directly upward, perpendicular to the ecliptic, to a distance no farther from the Sun than Earth's own orbit. Reaching the frozen worlds at the edge of the solar system is actually easier than reaching the seemingly empty space directly above the Sunday. The ecliptic is not a road that spacecraft simply follow. It is a moving current that everything in the solar system has shared for billions of years. Escaping that current is many times more difficult than continuing to travel within it. The reason this seems so surprising comes down to geometry. To travel outward, a spacecraft only needs to increase its speed slightly in the same direction it is already moving. That small increase gradually stretches its orbit into a long ellipse that can extend toward Jupiter, Saturn, or even Pluto. This is the smooth and fuel-efficient strategy used by almost every mission sent to the outer solar system. The Sun's gravity performs most of the work needed for the journey. The spacecraft only has to provide a modest push at exactly the right time, allowing its new orbit to carry it the rest of the way. To travel upward, a spacecraft must generate velocity at a right angle to the motion it already has. Its existing speed provides no assistance at all. The Sun's gravity cannot help with this climb either, because it always pulls inward toward the Sun rather than downward out of the plane. Every kilometer, S of vertical speed, must be earned entirely through fuel burned in space with no natural shortcut available. That is the fundamental reason why, in terms of spaceflight, the Sun's polar regions are even harder to reach than the outer planets. They are not especially distant. The Sun's poles lie at nearly the same distance from Earth as every other part of the Sunday. What makes them so difficult to visit is that reaching them requires escaping the flat orbital plane into which gravity organized nearly everything 4.5 billion years ago. The structure of the solar system naturally favors anything moving along its existing flow while resisting anything trying to cross it. In that sense, the Sun's poles occupy an unfriendly destination. They exist in a part of space that the solar system itself rarely enters. There is, however, a way to overcome the delta V barrier, and it is the same technique that has supported nearly every major deep space mission during the last 60 years. If a spacecraft follows a carefully planned trajectory, it can pass close to a planet and use that planet's gravity to change its direction or alter its speed relative to the Sun without burning additional fuel. Because the planet is unimaginably more massive, it gives up or receives only an almost undetectable amount of orbital speed in return. Energy remains perfectly conserved. The spacecraft temporarily takes a tiny fraction of the planet's orbital energy, while the planet loses an amount so small that it cannot realistically be measured. This maneuver is known as a gravity assist, a planetary flyby, or a swing-by, and it is about as close as physics comes to offering a free lunch. One carefully executed flyby can alter a spacecraft's speed by several kilometers, S, during a single encounter, depending on the planet's mass, the relative encounter speed, and the exact geometry of the approach. More massive planets provide stronger boosts. Higher encounter speeds allow greater changes in direction. The angle at which the spacecraft passes the planet determines whether the resulting change increases its existing speed, decreases it, or redirects it sideways. By arranging several flybys with precise timing, an experienced trajectory designer can build flight paths that no practical amount of rocket fuel could ever achieve on its own. Jupiter, being the largest and most massive planet, serves as the most powerful natural slingshot in the entire solar system. A close encounter with Jupiter can change a spacecraft's speed by 10 kilometers per second or even more during a single pass. If the approach geometry is chosen correctly, Jupiter can hurl the spacecraft completely out of the planetary plane, sharply redirecting its path upward or downward relative to the ecliptic. The required delta V is essentially zero. The real challenge lies in mission planning, because the spacecraft must arrive at Jupiter at precisely the right moment and from exactly the correct angle to leave on the intended trajectory. The launch opportunity is limited, and once the spacecraft commits to that path, changing it later becomes extremely difficult. Venus, although much smaller, offers another useful advantage because it is relatively close. Instead of providing one dramatic change, Venus can gradually reshape a trajectory through a series of repeated flybys. Each encounter increases the spacecraft's inclination by a small amount. Inclination is simply the technical name for how much an orbit is tilted compared with a chosen reference plane. By repeatedly traveling between an inner solar orbit and Venus, a spacecraft can slowly build more inclination, one flyby after another, until it steadily climbs away from the ecliptic over many years. This approach takes time, but it rewards patience, and patience requires no additional delta V. Instead of paying with enormous amounts of fuel, the spacecraft pays with years added to the mission. Gravity assists never break the laws of physics. Energy remains conserved. Momentum remains conserved. The spacecraft borrows a small amount of orbital energy from the planet, while the planet gives up an unimaginably tiny fraction in return. Across multiple flybys, this exchange becomes the deciding factor between a mission capable of reaching the sun's poles and one that never can. Nearly every long-distance mission ever sent towards the outer solar system has relied on at least one gravity assist along its journey. In a very real sense, this technique is what makes exploration of the solar system possible. There is a classic question in celestial mechanics that perfectly illustrates how difficult it is to travel between two locations in space. It asks, given a starting point, a destination, and a fixed travel time, what orbit can successfully connect them? Within the flat planetary plane, mathematics provides elegant solutions because nearly everything moves in the same direction and at reasonably compatible speeds. Once the path leaves that plane, however, the challenge becomes much greater because the connecting orbit must work against every natural advantage that normally exists. There is no need to spend time on the mathematics itself. The important idea is simple. The universe makes travel relatively easy between objects that share the same orbital plane, but much harder between an object and an empty location in space that lies outside that plane. The geometry favors remaining inside the disk and imposes a penalty on anything attempting to leave it. This is the fundamental reason why mission planners, when comparing possible destinations, almost always consider the sun's polar regions to be much more difficult to reach than the icy worlds scattered along the outer edge of the solar system. Those frozen worlds remain inside the planetary disk. The sun's poles do not. Traveling within the disk is naturally supported by the structure of the solar system, while trying to leave that flat region demands far more energy. Nothing in the universe prevents such a journey. It simply requires more energy than today's rockets can provide in one direct climb. Every spacecraft that has successfully risen far above the planetary plane has relied on planets as stepping stones, trading additional time and more complicated flight paths for the delta V it could not carry from launch. In many ways, the story of exploring the solar system is the story of finding clever solutions to this single challenge. Missions heading toward the inner planets take advantage of existing orbital paths and make relatively small adjustments along the way. Missions bound for the outer planets also follow those natural orbital routes while using gravity assists to cover the enormous distances. Missions that hope to leave the planetary plane must combine both of these methods and add another ingredient: patience. Every familiar flight profile has been shaped by the fact that the solar system is remarkably flat, and that flatness is reinforced by the enormous sideways speed every spacecraft inherits the instant it leaves Earth. The planetary plane is not simply a description of where the planets happen to orbit. It acts as a structural limitation that every space mission must work against. Even the vocabulary used by mission designers reflects this reality. Spacecraft are defined by their delta V budgets, their inclination limits, and the sequence of planetary flybys they perform. A trajectory is often identified not only by its destination, but by the way it curves, tilts, and uses gravity and time to gradually reshape its direction. A mission aimed at a planet within the disk can usually be explained in relatively simple terms. A mission designed to climb above the disk is described through multiple layers of planning, involving several phases, several gravity assists, and many years spent carefully reshaping its orbit. These two kinds of missions do not exist on the same kind of map. They belong to entirely different regions of engineering thought. In that sense, orbital velocity is not truly a prism. It is more like a powerful current. The entire solar system moves together around the sun within one broad, flat sheet of motion that has continued for billions of years. Traveling inside that flowing sheet is comparatively easy. Escaping from it is something else entirely. The mathematics involved are the same equations that govern every orbit. They are the same laws of angular momentum that flattened the original protoplanetary cloud. The same quiet physical rules repeating themselves from one scale to another. There is no enemy hidden within this geometry. There is only the long-lasting result of the way a solar system formed and preserved its shape. We exist inside that result, and every spacecraft humanity has launched exists within it as well. Rising above it is not beyond our reach. It simply calls for a very different style of mission from the ones we have carried out most often. Nearly everything humanity has learned about the sun has come from observing it near its equator. The sunspots visible in images captured from Earth, the solar flares recorded through ultraviolet observations, the slow movement of magnetic features across the sun's visible face, the bright coronal streamers revealed during total solar eclipses, and the decades of monitoring the one year activity cycle all come from this equatorial viewpoint. The sun's poles, where its axis of rotation meets its surface, remain largely hidden from Earth and from spacecraft that stay within the planetary plane. Even under the most favorable viewing conditions, the poles appear heavily foreshortened, seen only from a shallow angle and compressed against the curved surface of the star. To observe them clearly requires a position far above or below the sun itself. That viewpoint has existed for only a very small portion of the history of solar research. This fact is far more important than it may first appear, because the poles are not insignificant parts of the sunday. They're not simply distant edges or quiet regions that can be overlooked. They are the birthplace of some of the sun's most remarkable behavior. They are where the fastest streams of the solar wind begin. They are where the sun's global magnetic field flips every 11 years. They are also where much of the long-term engine-driving solar activity seems to operate. Many of the changes we observe from the sun's equator are actually visible effects of processes that begin at the poles. Ignoring the poles is like studying the symptoms of a condition while never examining its true source. The key idea that begins this discussion is the coronal hole. A coronal hole is an area within the sun's outer atmosphere, known as the corona, where magnetic field lines do not bend back toward the surface. Instead, they stretch outward into space. Through these open magnetic pathways, the corona's plasma, the extremely hot ionized gas that fills the sun's outer atmosphere, is able to stream freely away from the sun without obstruction. Coronal holes show up as dark regions in ultraviolet images of the sun because the plasma inside them is much less dense than the plasma found in the surrounding closed magnetic loop regions. In the corona, dark simply means the material is thinner, not colder or empty. During the quiet stages of the sun's one-year solar cycle, long-lasting coronal holes cover both polar regions. These are broad, stable, continuous features that can remain almost unchanged for years. The well-known fast solar wind is released from these polar coronal holes. Flowing outward from the poles, this wind reaches speeds of about 700 to 800 kilometers per second. That is nearly twice as fast as the slower solar wind produced closer to the sun's equatorial regions. The fast solar wind also differs chemically from the slow solar wind, showing slightly different proportions of elements and ionization states that reveal the different environments where each type of wind is created. By contrast, the slow solar wind moves outward at approximately 300 to 500 kilometers per second. It forms along the edges of coronal holes and in a region near the equator known as the streamer belt, where the sun's magnetic field creates the bright looping structures that become visible during a total solar eclipse. Compared with the fast wind, the slow wind is more chaotic, changes more in density, and has a less consistent chemical composition. Both forms of solar wind travel together through the heliosphere. The slow solar wind moves outward at approximately 300 to 500 kilometers per second. It forms along the edges of coronal holes and in a region near the equator known as the streamer belt, where the sun's magnetic field creates the bright looping structures that become visible during a total solar eclipse. Compared with the fast wind, the slow wind is more chaotic, changes more in density, and has a less consistent chemical composition. Both forms of solar wind travel together through the heliosphere, passing Earth and the other planets in alternating streams as the sun rotates and different regions gradually turn toward the planets, where the fast wind flowing from the polar regions meets the slower wind coming from the equatorial regions. The sun's magnetic field creates a thin, wavy boundary that spirals outward across the entire solar system. This boundary separates regions with opposite magnetic polarity, north on one side and south on the other, while the sun's rotation twists it into a long spiral that slowly turns through space. It is often compared to a ballerina's skirt because as the sun spins, the edge of the skirt rises and falls around the ecliptic, sweeping past the planets in a steady, repeating pattern. The formal name for this immense structure is the heliospheric current sheet, and it is the largest single magnetic structure anywhere in the solar system. Earth passes through the heliospheric current sheet several times during every solar rotation. Each passage causes small but measurable changes in the magnetic environment surrounding our planet. When these crossings occur during periods of increased solar activity, they can contribute to minor geomagnetic disturbances. The current sheet cannot be seen directly with the human eye. Instead, scientists map it indirectly using spacecraft that cross through it and record the local magnetic field, along with ground-based observations of the solar corona that allow researchers to estimate the sheet's shape from the visible streamer structures. The size of the ripples in the current sheet grows and shrinks throughout the solar cycle. Around solar maximum, when the sun is at its most active and its magnetic field is highly disordered, the sheet becomes strongly tilted, with large peaks and deep troughs extending far above and below the equator. Near solar minimum, when solar activity is at its weakest, the sheet becomes much flatter, lying close to the plane of the solar equator. This changing shape is one of the slow, steady rhythms of the heliosphere, repeating gently over many years. Seen from high above the sun, the heliospheric current sheet would likely be one of the most remarkable sights in the entire solar system. It would appear as a vast magnetic surface that slowly rotates and continuously changes shape while stretching far beyond the planets, rising and falling with the sun's changing seasons and revealing the overall condition of the solar dynamo across every distance. No spacecraft has ever captured a direct image of the current sheet. Its structure has only been reconstructed from in situ measurements collected as spacecraft travel through it, and from observations of the solar corona made from within the planetary plane. A true view from above would reveal, for the first time, its actual three-dimensional form and show exactly how it changes as the sun's magnetic activity evolves. About every 11 years, the sun's magnetic field flips completely. The magnetic North Pole becomes the magnetic South Pole, and the magnetic South Pole becomes the magnetic North Pole. This marks one half of the complete 2-2-year magnetic cycle, sometimes called the Hale cycle, which appears to control much of the activity observed on the Sunday, the changing number of sunspots, the power and frequency of solar flares, the structure of the corona, and the size and shape of the polar coronal holes all follow this magnetic rhythm. The reversal does not occur instantly. Instead, it develops gradually over several years as the cycle progresses. The process begins in the polar regions. Throughout each cycle, magnetic flux carrying the new opposite polarity slowly moves from active regions at lower latitudes toward the poles. Sunspots and active regions usually appear in pairs with opposite magnetic polarities, and one polarity consistently leads the other as those regions move across the visible face of the Sunday. Over the years, the trailing magnetic polarity slowly drifts toward the poles through diffusion and gradual surface flows. As enough magnetic flux with the opposite polarity gathers near a pole, it neutralizes the existing polar magnetic field, causing the sun's global magnetic polarity to reverse. This reversal does not always happen simultaneously at both poles. One pole can complete the transition months or even years before the other. During that temporary period, the sun's overall magnetic structure is no longer a simple dipole. Instead, it behaves more like a quadrupole, with several magnetic poles appearing at unusual latitudes. Eventually, the second pole finishes the reversal, restoring the sun to a stable dipole configuration, now with its magnetic orientation completely reversed. From the gradual buildup of fresh magnetic flux to the final stabilization of the reversed field, the entire sequence occupies most of the one-year solar cycle. The strength of the sun's polar magnetic field near the end of one cycle appears to be an important indicator of how active the following cycle will become. A powerful polar field is usually followed by a strong sunspot cycle 11 years later, while a weak polar field is often followed by a quieter cycle. Although this relationship is not an absolute rule and scientists are still studying the exact physical process behind it, the connection is consistent enough that astronomers consider measurements of the polar magnetic field to be among the most dependable tools for predicting future solar activity. In that sense, the poles truly function as the sun's dynamo room. The dramatic events seen around the equator are the visible outcome, while the underlying source lies hidden at the high latitudes that remain difficult to observe. The limited images that have been captured of the polar regions, although taken from only partial viewing angles and at modest resolution, already suggest that the poles look very different from the equator. Large sunspots are absent there. Instead, the magnetic field seems to divide into countless tiny concentrations of magnetic flux, forming a fine, tangled web across the surface. The visible texture of the solar surface near the poles is unlike that of the equatorial regions. Rather than broad active regions and massive sunspot groups, the poles are dominated by much smaller and less organized magnetic structures. Long, narrow streams of plasma, known as polar plumes, stretch outward from the polar regions, resembling blades of grass following the direction of open magnetic field lines. These plumes are easiest to observe during total solar eclipses, when the sun's bright surface is briefly covered and its faint corona becomes visible. Viewed from within the plane of the solar system, the plumes appear as soft rays bending away from the sun's polar edges. If they could be seen directly from above a pole, they would form a pattern of rays spreading outward in every direction along the open magnetic field. Each plume would appear as a slender column of slightly denser plasma flowing through the surrounding fast solar wind. Imagine looking at the sun not as a flat circle, but as a complete sphere seen from above its axis of rotation. Instead of the familiar dark sunspots clustered around the equator, you would see a calm, granular surface covered with delicate plumes spreading outward like the petals of a slowly turning flower. The powerful, fast solar wind would stream away in long, nearly straight beams. From that viewpoint, the sun would feel less like the image people usually recognize and more like the wide open eye of something ancient, quiet, and endlessly patient. Its magnetic field will be exposed in a way that no equatorial perspective can fully reveal. The poles also play a central role in preserving the sun's long-term magnetic memory. Not every magnetic reversal cycle unfolds with the same strength. Some cycles are much more active than others. There have even been periods lasting for centuries when the sun entered unusually quiet phases, producing weaker sunspot cycles and calmer magnetic activity. These prolonged intervals of reduced activity appear to be linked to weak polar magnetic fields that persist across many successive cycles. Variations in the sun's behavior over decades and even centuries seem to begin just like the regular solar cycle itself, with the slow build-up and gradual decay of magnetic flux at the poles. Even the overall pattern of the sun's magnetic eruptions reflects the influence of its polar regions. Large filaments and prominences that occasionally erupt from the solar surface usually develop along the boundaries separating regions of opposite magnetic polarity. As magnetic fields gradually migrate toward the poles throughout each cycle, these boundary lines shift with them, causing the locations of major eruptions to move across different latitudes over time. When astronomers map this behavior across many solar cycles, it produces the well-known butterfly diagram of solar activity, where sunspot bands first emerge at higher latitudes early in each cycle, before steadily drifting toward the equator as the cycle progresses. Every part of this visible pattern can be traced back to processes that begin at the poles and eventually return there. The poles are where magnetic fields gather, where they reverse direction, where the fast solar wind begins, and where the sun stores the long-term magnetic memory that shapes its future behavior. They are the most active locations for the most basic processes in solar physics. At the same time, they remain the places we understand the least because spacecraft have visited them only on rare occasions. The polar coronal holes are extraordinary features on their own, and they deserve a closer and more thoughtful look. During the quietest part of the solar cycle, a polar coronal hole can spread across a huge portion of the sun's northern or southern hemisphere. When viewed in ultraviolet wavelengths, the dark area stretches from the pole itself to roughly 60 degrees of latitude, and sometimes even beyond that. The edges of these holes are neither neat nor uniform. Instead, they twist and wander across the high latitudes, with inlets and extensions of open magnetic field reaching into the surrounding corona filled with closed magnetic loops. Their outlines continue to change over the course of weeks and months. Yet the presence of a large polar coronal hole during solar minimum remains one of the most stable and recognizable features of the sun's behavior. As the solar cycle gradually moves toward its maximum, these polar coronal holes begin to shrink. The movement of magnetic flux with opposite polarity toward the poles, the growing complexity of magnetic fields at lower latitudes, and the gradual cancellation and reversal of the polar magnetic field all work together to break apart the polar holes during the active stage of the cycle. By the time solar maximum arrives, the polar holes may almost disappear completely, while smaller and isolated coronal holes appear across different latitudes instead. Once the magnetic field reversal has finished, the polar holes slowly form again with the opposite magnetic polarity. They continue expanding until they once again reach their greatest size as the next solar minimum approaches. The fast solar wind flowing outward from these polar holes also carries a distinctive chemical signature in the heavier elements it contains. The abundance of certain elements in the fast solar wind differs from that found in the slower solar wind, reflecting the different environments where each type begins. The slow solar wind, which comes from the closed magnetic loops at lower latitudes, has a composition that has been altered through long periods of interaction within the corona, causing some elements to become more abundant than others. By comparison, the fast solar wind escapes much more directly along the open magnetic field lines of the polar holes, preserving a composition that more closely matches the material found in the sun's visible photosphere. These differences in composition are small but measurable, allowing astronomers to identify the most likely source region on the sun for a particular stream of solar wind. Whenever the polar surface can be observed in enough detail, it displays the same familiar granulation pattern seen across the rest of the sunday. This granulation is the visible result of convection taking place beneath the surface. Hot plasma rises through the bright centers of countless convection cells, while cooler plasma sinks back down along their darker boundaries. Above this granulated surface near the poles, magnetic field lines rise upward in countless narrow bundles. Each one marks a location where concentrated magnetic flux has emerged from the convective layer into the corona overhead. These bundles combine to form the much larger plume structures that extend outward into space, and together those plumes create the distinctive texture of the polar corona that becomes visible during total solar eclipses or through observations made by spacecraft traveling at high inclinations. The polar regions also contribute in a quieter but equally important way to the sun's rotation. The sun does not spin like a solid object. Its equator turns more quickly than its poles, completing a rotation in about 25 days near the equator, while the high latitudes require more than 30 days to complete the same journey. This behavior is known as differential rotation, and it serves as one of the key mechanisms that gradually twists and strengthens the sun's magnetic field throughout each solar cycle. Because the equatorial regions rotate faster than the polar regions, magnetic field lines become stretched and wound around the sun, creating increasingly tangled magnetic structures that eventually give rise to sunspots, solar flares, and finally, the reversal of the polar magnetic field. In this way, the poles define one end of the differential rotation pattern that powers the entire solar cycle. Hidden beneath the visible surface, the sun's deep interior also rotates differentially. Scientists investigate these internal motions by studying the sun's natural oscillations, which reveal how different layers move below the surface. The rotation patterns inside the sun vary with both latitude and depth, and researchers believe that the boundaries separating regions with different rotation speeds are the places where the strongest magnetic fields are generated. The polar regions are part of this deep internal structure as well, although many of the finer details are still not fully understood. Taken as a whole, the sun's magnetic activity follows a long sequence of connected processes. It begins deep inside the sun, moves upward through the convective layers, appears on the surface as sunspots and active regions, slowly migrates poleward over many years, and eventually gathers at the poles, where the magnetic field reverses and prepares the next solar cycle. The poles are the final destination of this long journey and the place where the memory of one solar cycle is preserved before the next one begins. The explanation for this missing view comes back to the geometry discussed in part 2. From within the flat plane where the planets travel, the sun's poles are extremely difficult to observe clearly. Seeing them properly requires a spacecraft that can travel well above or below that plane, and missions capable of doing so have been exceptionally uncommon. The poles are not located at some impossible distance. Instead, they remain out of reach for the types of spacecraft that have shaped most of the history of space exploration. For billions of years, the sun has continued rotating, flipping its magnetic field, producing eruptions, and releasing its polar solar wind without anyone observing these processes from the directions where the geometry matters most. The next part focuses on the only two missions that, in their own different ways, have attempted to close this long-standing gap. Throughout the entire history of spaceflight, only two spacecraft have ever traveled significantly beyond the ecliptic to observe the sun's polar regions directly. Each mission is extraordinary, yet each provides only part of the complete picture. The first mission reached high solar latitudes, but did not carry a camera capable of taking direct photographs of the sun's surface. The second mission is still in progress, slowly increasing the tilt of its orbit through repeated flybys of an inner planet, and has only very recently returned the first close-up direct images ever captured of one of the sun's poles by any spacecraft. Together, these two missions make up the full extent of humanity's experience above the planetary plane. Neither spacecraft has ever remained stationary over the poles. Both have continued moving along their paths, gathering observations for a limited time before their orbits carried them away across another part of the solar disk. The first spacecraft to leave the ecliptic in a meaningful way was the result of a long-term collaboration between a North American space agency and a European space agency. After years of planning, it was launched from low Earth orbit aboard a winged orbital vehicle. Compared with many interplanetary probes, the spacecraft was relatively compact. It featured one large communication dish and a spinning body that kept its scientific instruments evenly exposed to the sun during flight. Its payload included instruments designed to study magnetic fields, particles within the solar wind, energetic ions, dust, radio emissions, and cosmic ray populations found at high solar latitudes. What it lacked, however, was a high-resolution imaging system. No camera on board was capable of photographing the sun's visible surface or revealing the fine details of its corona. Its mission was to measure the polar environment directly rather than produce images of it. The flight path chosen for this mission remains one of the most elegant examples of orbital design ever achieved. Instead of heading inward toward the Sun after leaving Earth, the spacecraft first travelled outward on a long, curved journey toward Jupiter. At precisely the right moment, it passed close to Jupiter, allowing the giant planet's immense gravity to redirect its path sharply away from the ecliptic. After that encounter, the spacecraft's orbit became tilted by about 80 degrees relative to the ecliptic, placing it on a path that was almost perpendicular to the plane, followed by nearly every other major object in the solar system. It then continued circling the Sun along this steeply inclined orbit, rising far above the ecliptic during one part of each revolution and descending far below it during the opposite part. This achievement was remarkable because no chemical rocket alone could have performed such a maneuver directly. Producing an orbital inclination change of 80 degrees after departing low Earth orbit would have required many tens of kilometers, s, of delta V, a performance well beyond the capability of any chemical launch system ever built. By making the long journey out to Jupiter first, the spacecraft allowed Jupiter's gravity to supply almost the entire inclination change at essentially no fuel cost. Although this indirect route required several additional years compared with a hypothetical direct ascent, it succeeded in accomplishing something that a direct climb simply could not achieve. It became the first practical proof that reaching the Sun's polar regions, while extremely expensive in terms of delta V, was nevertheless possible when planetary gravity was used with enough creativity and precision. The scientific results from this first mission were extensive. For the first time, direct in situ measurements confirmed that the fast solar wind originates mainly from the Sun's polar regions, while the slower solar wind is produced primarily at lower latitudes. Before these observations, scientists had inferred the different origins of the two solar wind regimes using ground-based observations together with theoretical models. However, no spacecraft had ever travelled above the planetary plane to verify those ideas directly. During its passes over both polar regions, the spacecraft measured the speed, composition, and magnetic structure of the solar wind it encountered. The fast solar wind appeared exactly where existing models had predicted it should be. The mission also confirmed that the heliospheric current sheet truly surrounds the Sun in the same way it had previously been compared to the shape of a ballerina's skirt. As the spacecraft climbed toward higher latitudes, it crossed the current sheet less and less often, precisely matching expectations for a structure centered near the Sun's equator and only gently warped into higher latitudes. For the first time, scientists were able to map the shape of the heliospheric current sheet as it changed with both solar latitude and different stages of the solar cycle from a position that could truly observe how its form varied above the plane of the planets. An even more surprising result from the first mission involved the large-scale organization of the Sun's magnetic field farther from its surface, especially around the polar regions. Near the Sun, the magnetic field behaved much as earlier surface observations had predicted. Distinct open magnetic field lines extended outward from the polar coronal holes. However, at greater distances from the Sun, the magnetic field became unexpectedly consistent across different latitudes. After the spacecraft traveled beyond the immediate polar areas, the radial component of the magnetic field was found to be nearly identical in every direction. This happened because the outward flowing solar wind carries magnetic fields throughout the heliosphere, gradually smoothing out many of the differences. In other words, the magnetic field turned out to be more localized close to the Sun than expected, yet much more uniform on larger scales than researchers had anticipated. The first mission also explored regions that no previous spacecraft had ever entered. High above the sun, far beyond the flat plane occupied by the planets. It measured cosmic rays, interstellar dust particles drifting into the solar system from deep space, and energetic particles generated by solar activity in environments that had never before been examined directly. Measurements of cosmic ray intensity at high heliospheric latitudes gave astronomers valuable insight into how galactic cosmic rays enter the heliosphere from above, answering questions that simply could not be investigated from spacecraft remaining within the planetary plane, where the geometry is entirely different. The mission continued operating for nearly 2 decades before its instruments finally became silent and the mission was officially brought to an end. Even today, the orbit it established still carries it above and below the sun, although the spacecraft itself is now lifeless. Its systems are inactive, and the communication dish that once sent signals back to Earth no longer transmits anything. That orbit remains one of the most remarkable achievements in the history of space exploration. It is a permanent, high-inclination path around the sun, with the silent spacecraft continuing its endless journey for as long as gravity preserves the orbit. No rescue mission has ever been planned, and no replacement spacecraft has followed the exact same route. Despite everything the first mission accomplished scientifically, there was one major thing it could not provide: photographs. It successfully measured the solar wind, yet it could not capture images of the sun's surface from above. It measured the magnetic field around the poles, but it could not directly photograph the magnetic structures themselves. As a result, the true appearance of the sun's polar regions, including the polar surface and the polar corona, remained largely unknown after the mission ended. Until very recently, the closest thing scientists had to a polar image was a heavily foreshortened view taken from within the ecliptic plane, where the sun's pole was tilted only slightly toward the observer, and much of the fine detail disappeared because of the viewing angle across the curved edge of the sunday. Many years later, a new mission, led by Europe, was launched with a completely different approach. Rather than relying on a single gravity assist from Jupiter to permanently tilt its orbit, this spacecraft gradually changes its path through a series of repeated flybys of Venus. Each encounter with Venus increases the spacecraft's orbital inclination by a small amount. The process is slow and deliberate. Every flyby contributes only a few additional degrees of tilt. Yet after many years and numerous encounters with Venus, the spacecraft steadily rises farther above the planetary plane, reaching increasingly higher solar latitudes with every orbit around the sunday. Unlike its predecessor, this spacecraft carries a complete collection of imaging instruments, specifically chosen to fill the gaps left by the earlier mission. It includes a high-resolution telescope capable of photographing the sun's visible surface in remarkable detail. A magnetograph directly measures the magnetic fields across the solar surface latitude by latitude. Ultraviolet imaging instruments reveal the structure of both the chromosphere and the corona at wavelengths, where the hot coronal plasma shines most brightly. Coronagraphs block the brilliant solar disk so they can capture detailed images of the faint outer corona. Additional instruments directly sample the surrounding solar wind and magnetic environment, providing in situ measurements that perfectly complement the remote observations. Together, these systems turn the spacecraft into a true orbiting solar observatory, finally allowing scientists to study the sun's polar regions with the same level of detail that the equatorial regions have enjoyed for decades. At perihelion, the point where its orbit brings it closest to the sun, the spacecraft travels near enough that controlling heat becomes one of the most critical engineering challenges. A specially designed heat shield protects its scientific instruments from the intense solar radiation encountered during these close approaches. The shield also includes small protective doors that open briefly whenever the spacecraft is far enough from the sun to allow its optical instruments to observe safely. The heat shield itself was built with a carefully designed surface coating that reflects as much incoming sunlight as possible, allowing the rest of the spacecraft to remain cool enough for its systems to operate safely. Coping with the intense heat is a major engineering challenge, but it is one that can be overcome, and repeated close passes have already shown that the design performs as intended. In recent years, the spacecraft has started reaching the orbital inclinations necessary to observe the Sun's polar regions directly. For the first time, close-up images of one of the Sun's poles have been successfully returned. Earlier observations made by spacecraft travelling within the ecliptic plane suffered from the problem of foreshortening, which limited what could actually be seen. These new images, captured from above the plane, reveal the polar surface and the polar corona from an angle that finally makes their true structures visible in meaningful detail. Over the coming years, the spacecraft is expected to increase its inclination even further, eventually obtaining full views of both solar poles. When the first images of the Sun's southern polar region arrived, they looked nothing like the familiar equatorial view. The texture across the surface appeared much finer and noticeably more irregular. Instead of organized magnetic patterns, the magnetic field formed a tangled network filled with countless tiny concentrations of magnetic flux, rather than the large active regions commonly found around the equator. The polar plumes could now be distinguished as individual streams of plasma stretching outward from the polar coronal hole, gently bending with the curved shape of the rotating magnetic field. It marked the first occasion that humanity had ever viewed the Sun from this direction with truly useful resolution. No earlier archive contains detailed footage of the Sun's poles. Such images simply did not exist. Together, the two missions have revealed facts that could never have been discovered by remaining within the ecliptic plane alone. The earlier mission confirmed that the polar regions operate differently from the equatorial regions, with different solar wind behavior, different magnetic field properties, and a different particle environment. The present mission is now providing the information that the earlier mission could not: direct images, detailed magnetic maps, ultraviolet views of the polar corona, and clear observations of the appearance of the polar surface itself. Combined, these missions have shown that observing the Sun from above the ecliptic is not merely an added benefit for solar research. It is essential if scientists want to understand the Sun as a fully three-dimensional object, instead of the flat-looking disk seen in every photograph taken from near the equatorial plane. Even so, despite the achievements of both missions together, they have explored only a small portion of what a dedicated polar observatory could eventually measure. Neither spacecraft has been capable of remaining above a solar pole while the Sun slowly rotated beneath it. Instead, both have continued along their own inclined paths, passing through the polar regions only during the brief periods when their orbits carried them to sufficiently high latitudes, before descending once again toward lower latitudes as their orbital cycles continued. A spacecraft able to stay positioned above one pole continuously for years has not yet been developed. The complete story of the Sun's polar regions, which would require long-term observations from a true polar viewpoint, still remains unwritten. The progress made so far is extraordinary when compared with the many decades during which no polar observations existed at all. At the same time, the amount still left to discover is just as enormous when measured against what a permanent polar mission could accomplish. Both of these realities exist together. These two missions have opened a window toward a perspective that remained inaccessible throughout the entire history of solar physics. Yet they also represent only the earlier step into a region that, by almost any reasonable standard, is still largely unexplored. Humanity has briefly visited the Sun's poles. It has not yet stayed there long enough to truly know them. The scientific instruments carried by each of these missions also deserve careful attention, because the collection of instruments ultimately determines the kinds of scientific discoveries any spacecraft is capable of making. The instruments aboard the first mission were selected to study the polar environment by measuring its physical properties, including the strength and direction of the magnetic field at high solar latitudes, the density and speed of particles carried by the solar wind, the composition of energetic ions, the populations of cosmic rays, the radio signals generated by different plasma processes, and the tiny dust particles drifting through interplanetary space. Every one of these observations depended on a separate instrument carefully designed to detect a specific type of particle, electromagnetic wave, or magnetic field. In many ways, the spacecraft functioned as a traveling physics laboratory, carrying scientific equipment into regions where no laboratory had ever operated before. The magnetic field instrument used on the first mission was a device known as a flux gate magnetometer, a highly precise sensor capable of measuring both the strength and the direction of magnetic fields. To reduce interference from the spacecraft's own electrical systems, the magnetometer was installed on the end of a long boom, extending outward from the spacecraft's main structure, placing it as far away from onboard electronics as possible. The boom was unfolded soon after launch and stayed fully extended for the entire mission. At its far end sat the magnetometer, continuously recording the local magnetic field as the spacecraft traveled through different parts of the heliosphere. The measurements it collected became one of the most complete and continuous records of magnetic field data ever gathered across such a broad span of solar latitudes. The particle instruments on the first mission consisted of several detectors, each designed to observe different energy levels. They measured everything from the relatively cool particles carried by the solar wind to the higher energy ions created by solar flares and shock waves, and even the extremely energetic galactic cosmic rays entering the heliosphere from interstellar space. Every detector counted incoming particles, measured their energy, and in some cases identified the chemical elements they contained. Together, these observations created the first truly complete view of the particle environment at high heliospheric latitudes, covering the full energy spectrum and extending across more than a complete solar cycle. The first mission also carried a dust instrument based on a piezo electric detector that could detect the impact of individual dust grains striking the spacecraft. Every collision generated a tiny electrical pulse whose strength depended on the mass of the incoming grain. By recording these impacts and studying their properties, the instrument gradually revealed the nature of the dust environment in interplanetary space at latitudes well above and below the ecliptic plane, where no direct measurements previously existed. Among its discoveries was clear evidence of interstellar dust entering the solar system from beyond its boundaries, identifiable from ordinary solar system dust by the way it moved and by its physical characteristics. The radio and plasma wave instrument aboard the first mission measured the low-frequency electromagnetic waves and plasma oscillations that spread throughout the heliosphere. These signals contain valuable information about processes ranging from disturbances produced by solar flares to long-distance interactions between the solar wind and the outer boundary of the heliosphere far beyond the planetary orbits. The instrument recorded the radio signatures produced by shock fronts moving outward through the heliosphere, and on several occasions even detected signals linked to the distant region where the solar wind encounters the interstellar medium. The current mission follows a different design philosophy for its scientific payload. It carries the same kinds of in situ instruments found on the first mission, while also adding imaging instruments that were not available before. Its visible light telescope can resolve details on the sun's surface, measuring only a few hundred kilometers across, approaching the finest level of detail normally achieved by ground-based telescopes during the rare periods of exceptionally stable atmospheric conditions. The magnetograph directly maps the magnetic field across the visible surface of the Sun, producing images that immediately display both the strength and direction of the magnetic field at every location. Ultraviolet imagers observe the corona at the wavelengths where its extremely hot plasma shines most brightly, exposing the shapes of magnetic loops, the positions of active regions, and the edges of coronal holes. The current mission's coronagraphs use a small occulting disk to hide the brilliant photosphere, making it possible to photograph the much fainter corona in white light. This technique is the same one responsible for the spectacular views of the solar corona during total solar eclipses, but it allows continuous observation instead of limiting scientists to the brief minutes when a natural eclipse occurs. By combining the magnetograph, the ultraviolet images, and the coronagraphs, the mission builds a layered view of the Sun that stretches from its visible surface through the chromosphere and into the corona, with every region being observed at the same time by a single spacecraft. Once the orbit of the current mission becomes tilted enough to provide a clear view of the Sun's polar regions, every one of these instruments shifts its attention toward this new perspective: the polar surface, the polar magnetic field, the polar corona, and the surrounding plasma environment near the spacecraft are all measured together using the same coordinated approach that spacecraft within the ecliptic plane have long used to study the Sun's equatorial regions. This marks the beginning of a scientific archive dedicated to the Sun's poles, comparable in its purpose, though not yet in its size, to the enormous collection of observations gathered from the equatorial regions over more than a century of solar research. Even after combining the data from both missions, observations of the solar poles still represent only a small portion of the much larger equatorial archive. The first mission remained active for nearly 2 decades, but its instruments were restricted to in situ measurements, and its orbit carried it through the polar regions for only a limited part of each orbital cycle. The current mission is still relatively young and has only recently reached the high solar latitudes required to begin detailed imaging of the polar regions. Its collection of images from the Sun's polar regions is still limited, although it continues to expand over time. A complete view of the Sun as a fully 3-dimensional object will only come together little by little, one image at a time and one measurement at a time, throughout the remaining years of the current mission and any future missions that may follow. This is slow work. The available information is limited, and the overall picture is still far from complete. The influence of the Sun extends well beyond the paths of the planets. The solar wind keeps traveling outward, becoming thinner as it spreads, while carrying the Sun's magnetic field across distances far larger than the planetary system itself. Eventually, this outward stream collides with the gas and dust of the local interstellar medium. At the point where the pressure of the solar wind and the pressure of the surrounding interstellar gas become equal, a boundary is created. The enormous bubble of solar plasma enclosed by that boundary and carved out by the Sun's wind is known as the heliosphere. The boundary itself is called the heliopause. Everything we recognize as our solar system, the planets, the asteroid belt, the Kuiper belt, and the vast inner regions of the comet cloud exists deep inside this enormous bubble. The heliosphere serves as our local space weather system, our nearby magnetic environment, and our protective shield against the much harsher conditions found in interstellar space. Even so, the true shape of the heliosphere remains one of the unanswered questions in modern astronomy. As with many of the mysteries explored tonight, the challenge comes from a simple limitation. Every observation we have made of the heliosphere has been taken from inside it, within the same flat planetary plane shared by the entire solar system. No one has ever viewed this bubble from the outside. No direct image has ever shown it from above. It has never been mapped from a position beyond the very structure that defines its shape. For many decades, scientists pictured the heliosphere as having the shape of a comet. The sun moves through the surrounding interstellar medium at a significant speed of roughly 26 kilometers per second relative to the nearby gas. Because of that motion, researchers believe the heliosphere would be compressed into a rounded front on the upwind side, where the moving sun pushes against the gas ahead of it while stretching into a long, narrowing tail on the downwind side. The idea resembled a comet traveling through space with a bright head leading the way and a long tail streaming behind it. This comet-like model came from calculations describing how the solar wind should interact with the interstellar gas surrounding it, along with observations of similar bubble-shaped structures surrounding other stars moving through the galaxy. The model successfully explained much of the evidence available at the time. It also produced clear predictions about where the upwind boundary should be located, how the magnetic field should behave near that boundary, and what the long downwind tail should look like. Throughout much of the late 20th century and into the early 21st century, this comet-shaped heliosphere remained the standard working model for our local cosmic bubble. 2 spacecraft launched many decades ago and still traveling away from the sun have now crossed the edge of the heliosphere and entered interstellar space. Their instruments have provided the closest thing we possess to direct measurements of the heliosphere's boundary. Even so, both spacecraft crossed that boundary near the upwind nose of the heliosphere and did so roughly within the same planetary plane. Neither spacecraft was able to observe the distant tail. Neither could examine the structure from above or below. Each could only measure the small region of the heliosphere that happened to lie along its own path. The information they returned proved to be far more detailed and much more surprising than the traditional comet-shaped model had expected. More recently, astronomers studying the interaction between the heliosphere and the surrounding interstellar magnetic field proposed a very different picture. Instead of forming one long trailing tail, this newer model suggests that the heliosphere looks more like a deflated croissant. It contains 2 curved lobes extending backward from the nose, connected by a narrow middle section with no long tail stretching into space. According to this interpretation, the sun's magnetic field, carried outward by the solar wind, becomes strong enough near the boundary to squeeze the bubble closed on the downwind side. That effect prevents the formation of the long tail predicted by the older comet model. In the croissant model, the heliosphere is smaller and more compact than previously imagined, with a shape that resembles a curved shell rather than an elongated teardrop flowing behind the sundae. This newer model also agrees with several measurements collected from inside the heliosphere, including the distribution of energetic neutral atoms, particles that travel inward from the boundary, and can be mapped without requiring a spacecraft to fly all the way to the edge itself. It also suggests that the boundary on the downwind side could sit much closer to the sun than the comet-like model predicts, perhaps only a little farther away than the boundary facing the incoming interstellar flow. This idea is still under discussion. The available observations remain limited. Reconstructing the overall shape is extremely difficult when relying only on measurements collected within the plane of the solar system. The actual answer may fall somewhere between these competing ideas, or it may turn out to be a completely different structure that neither model has predicted. There is something quietly humbling about the fact that no instrument, no telescope, and no spacecraft has ever viewed the heliosphere from outside its plane. For centuries, humanity has mapped the solar system one world at a time. Yet, the overall outline of our cosmic neighborhood, the gentle border that marks where the sun's influence ends and the rest of the galaxy begins, has never truly been drawn. We are still waiting for the first real portrait of our own cosmic home. We are still waiting for the first image of the vast bubble that surrounds us. We are still waiting to see the place where the solar wind gives way to the wind of interstellar space. To investigate many of these questions from inside the heliosphere without waiting for a spacecraft capable of leaving the planetary plane, scientists are preparing a planned interstellar mapping probe. This new spacecraft is intended to orbit relatively close to Earth while detecting energetic neutral atoms flowing inward from the heliospheric boundary across the entire sky. By carefully measuring both the arrival directions and the energies of these incoming particles, the mission can reconstruct the three-dimensional shape of the boundary without ever needing to travel there directly. In this way, the spacecraft will improve our understanding of the heliosphere from the inside, even though we still do not have the advantage of an external viewpoint. Energetic neutral atoms form when charged particles carried outward by the solar wind collide with neutral atoms drifting inward from the local interstellar medium. During this interaction, one particle loses an electron while the other gains it, creating a fast-moving neutral atom that is no longer controlled by magnetic fields and is therefore free to travel in a straight path back across the heliosphere. Some of these newly created neutral atoms head toward the inner solar system, where specially designed instruments are able to detect them. These arriving particles preserve information about the locations where the interactions originally occurred, meaning they also contain valuable clues about the shape of the heliospheric boundary itself. By measuring the directions and energies of incoming neutral atoms across the entire sky, the spacecraft gradually builds a three-dimensional map of that boundary. The method is somewhat similar to the way a medical imaging system creates pictures of structures inside the body by collecting particles arriving from many different directions. The shape of the boundary can therefore be reconstructed from the patterns of inward traveling neutral atoms, even though no spacecraft has physically visited that distant region. A similar approach was previously used with lower sensitivity by an earlier mission operating within the plane of the solar system. That mission produced the first all-sky maps of neutral atoms coming from the heliospheric boundary and uncovered an unexpected feature, a bright ribbon of enhanced neutral atom emissions stretching across the sky in a distinctive geometric pattern. Scientists are still working to fully understand the origin of that ribbon, but its discovery clearly showed that the boundary is more complex than the simplest models had predicted. The new spacecraft will provide a major improvement in resolution, creating much sharper maps of the heliospheric boundary and increasing the likelihood of distinguishing between the comet-shaped model and the croissant-shaped model. Although the energetic neutral atom technique is extremely valuable, it remains an indirect method. It reconstructs the bubble's outer edge through evidence rather than through direct observation. A spacecraft traveling far above the ecliptic could study the boundary firsthand, directly measure the magnetic field structure at high solar latitudes, and, if supplied with enough fuel and enough time, perhaps even leave the heliosphere by traveling perpendicular to the planetary disk, becoming the first mission ever to enter interstellar space from above or below the solar system. At present, however, no mission of that kind has received funding. The concept exists in mission studies and engineering plans. The spacecraft itself does not yet exist. The heliosphere is not fixed in size or shape. It slowly expands and contracts with the rhythm of the solar cycle. As the sun becomes more or less active during its one-year cycle, the pressure of the solar wind changes and the heliosphere responds. During solar maximum, when the solar wind grows stronger, the bubble expands outward and its boundary moves farther from the sunday. During solar minimum, when the solar wind weakens, the bubble contracts and the boundary shifts closer inward. The two spacecraft that have already crossed this boundary reached it during different stages of the solar cycle, and the distances they recorded reflected the changing conditions that existed at the time of each crossing. The interstellar environment surrounding our heliosphere is not perfectly uniform either. At present, the The Sun is traveling through a relatively small region of low-density interstellar gas known as the local interstellar cloud, which itself lies inside a much larger region of even lower density material called the local bubble. The local bubble is believed to have been formed by powerful supernova explosions that occurred tens of millions of years ago. Those ancient blasts pushed away the surrounding gas and dust, leaving behind a vast region of relatively thin material through which the Sun is now traveling. This means the boundary of our heliosphere exists inside one bubble that itself sits within a much larger bubble. The smaller bubble is created by the continuous flow of the Sun's solar wind, while the larger one was shaped long ago by exploding massive stars in our galactic neighborhood. As the Sun eventually leaves the local interstellar cloud and enters another part of the local interstellar medium, the conditions surrounding the heliosphere will change as well. If the surrounding interstellar material becomes denser, the heliosphere will be squeezed into a smaller volume. If the surrounding environment becomes less dense, the heliosphere will be able to spread farther outward. Its boundary is not a solid barrier. It is a point of balance, and that balance changes whenever the pressure outside changes. The heliosphere we live inside today matches the conditions that currently exist around us, and for most of recent solar history, it has remained close to its present size, aside from the slow variations that come with the solar cycle. The overall shape of the heliosphere is also influenced by the direction of the magnetic field that runs through the local interstellar medium. That magnetic field applies a measurable force along the heliosphere's outer boundary, and the direction of that force changes the shape of the boundary in ways that simple models without magnetic fields cannot fully explain. The croissant model depends partly on how the interstellar magnetic field interacts with the Sun's own magnetic field, where the boundary forms, while the comet model assumes a simpler structure in which magnetic effects play a much smaller part. Separating the influence of magnetic fields from the influence of gas pressure requires direct observations taken at or very close to the heliosphere's edge. So far, scientists have only obtained measurements from two boundary crossings, and both happened in roughly the same direction. Beyond the heliopause begins the true local interstellar medium. The space between stars is not completely empty. It contains extremely thin gas made mostly of hydrogen, tiny grains of dust, magnetic fields, and fast-moving energetic particles known as cosmic rays that are found throughout the Milky Way. The two spacecraft that cross the heliosphere's boundary are now directly measuring this interstellar region, providing the first in situ observations ever collected from outside our solar bubble. Even decades after they were launched, those spacecraft continue sending back valuable information at very slow transmission speeds across distances that increase every single day. Far beyond our immediate interstellar surroundings, the solar system continues its slow journey around the galaxy. Throughout hundreds of millions of years, the Sun has traveled through dense interstellar clouds, quieter regions, the spiral arms of the Milky Way, and the more open spaces between those spiral arms. Every one of these different environments has changed the heliosphere. Denser surroundings have compressed it, while thinner regions have allowed it to expand. The heliosphere we see today is only the latest version in a long sequence of heliospheres, each one shaped by the local conditions that existed during its own time. Take a quiet moment to picture exactly where we are. We live on a planet orbiting a star inside a bubble created by the solar wind, inside a region of interstellar gas, inside a much larger cavity left behind by ancient supernovae, inside one spiral arm of the Milky Way, inside the galactic disk, inside the local group where the Milky Way is the largest galaxy, and inside the far greater expanse of the nearby universe. Every layer surrounds another. Every layer has its own structure, its own physical rules, and its own long and quiet story. Tonight's question, the question of what exists above and below the sun, is really also a question about how well we are able to see these nested layers from our current location. From within the planetary plane, we observe them while looking through the dense disk that contains us. From far above that plane, our view would pass through much less material. The picture we have of our own home remains unfinished, not because the universe is too distant, but because humanity has viewed it from only one general direction. The viewpoint high above or far below the sun, the position from which the heliosphere could finally be seen in its entirety, has existed in principle ever since the original protoplanetary cloud collapsed. Yet instruments have reached that perspective only in the smallest and most incomplete ways. The complete portrait is still waiting. It has waited for an extraordinarily long time. It can continue waiting. That long wait is exactly what the next part of tonight's journey is about. We will explore what it would take to finally observe our solar system from the directions we have never truly observed before, and why spacecraft must rely on remarkable ingenuity to make that possible. There is a way to leave the flat plane shared by the planets without needing 30 kilometers per second of brute force delta V from low Earth orbit. The surprising solution is to first fall closer to the sun and only afterward perform the push that changes the spacecraft's path. It is one of the most elegant ideas in all of space flight, and in principle it has been understood ever since the earliest years of rocket science. At first this idea seems to go against common sense, but after you understand it, it feels as natural and unavoidable as a basic rule of geometry. When a spacecraft fires its engine deep inside the gravitational well of a massive object, it gains much more energy from that burn than it would if the exact same burn happened far away in open space. The explanation is simple. At the lowest part of the gravitational well, the spacecraft is already traveling at an extremely high speed, and the increase in kinetic energy depends on the square of that speed. Giving a small increase in velocity to something that is already moving very fast creates a much larger increase in energy than giving that same increase to something moving much more slowly. The fuel performs exactly the same chemical reaction in both situations. Yet the amount of useful energy gained is very different because the spacecraft's existing velocity magnifies the effect of the burn. In simple terms, burning 1 kilogram of propellant while traveling at 100 kilometers per second changes the spacecraft's total energy far more than burning that same 1 kilogram while traveling at only 10 kilometers per second. The fuel itself is exactly the same. The engine delivers the same thrust. The only thing that changes is the speed of the spacecraft at the moment the engine fires. That speed greatly increases the result because kinetic energy follows a squared relationship with velocity. This concept is commonly known as the deep well burn or the perihelion maneuver. It was formally described during the early years of rocket science by one of the pioneering figures in astronautics, whose work established many of the basic ideas behind modern orbital mechanics. The same rule has quietly guided every interplanetary mission ever launched. Whenever a spacecraft reaches a planet and needs to enter orbit, its engine is fired at the closest point of the flyby, known as periapsis, because that is where the spacecraft is moving the fastest and where every bit of fuel produces the greatest benefit. Likewise, when a spacecraft leaves a planet to begin a long journey outward, the departure burn is also carried out at the closest point of its orbit for exactly the same reason. The deep well principle has become one of the most important strategies for using fuel efficiently around any object with gravity. It becomes especially important in tonight's story because the sun creates the deepest gravitational well anywhere in the solar system. And An engine burn near the sun provides more energy than an identical burn performed anywhere else. When this principle is applied to the sun, it creates one of the boldest and most graceful maneuvers ever proposed for space travel. A spacecraft launched from Earth first falls inward toward the Sunday. As it descends, the sun's gravity accelerates it to tremendous speeds, well above 100 kilometers per second by the time it reaches its closest approach. At that point, known as perihelion, deep inside the sun's gravitational well, the spacecraft ignites its engine for a short but powerful burn. Because of the deep well effect, even a relatively small amount of fuel burned at that incredible speed produces a much larger increase in orbital energy than the exact same burn would have achieved near Earth's orbit. After completing the burn, the spacecraft begins climbing away from the sun once again, but it is now following a completely different path. If the burn is aimed in the correct direction, the new orbit can carry the spacecraft entirely out of the plane where the planets travel, reaching a trajectory that would otherwise require an almost impossible amount of energy. On paper, the maneuver is remarkably elegant. A relatively modest supply of fuel, burned at exactly the right time, can place a spacecraft into a polar orbit around the sun while requiring only a small fraction of the delta V needed for a direct climb away from Earth. The reduction is not small, it is enormous. A mission that might otherwise demand roughly 30 kilometers per second of direct perpendicular delta V can instead be achieved with only about 3 or 4 kilometers per second, if that velocity change is applied at the proper moment and in the proper direction. While passing close to the Sunday, once again, the geometry rewards working together with gravity instead of trying to overcome it. The challenge, however, is that the spacecraft must survive the extreme heat close to the sun, and this becomes the greatest engineering obstacle of the entire mission design. Near perihelion, the spacecraft is exposed to sunlight so intense that it can melt or seriously damage ordinary spacecraft materials. As it falls toward the sun, the temperature on the side facing the sunlight rises rapidly. To survive long enough to complete the perihelion burn, the spacecraft needs a highly specialized heat shield like those already proven by certain modern solar probes. These thermal difficulties are significant, but they are not impossible to solve. The required engineering already exists and has in that the maneuver demonstrated. The maneuver also depends on the spacecraft arriving at perihelion with its fuel still available. Very little fuel should be spent during the inward journey because any propellant burned early cannot take advantage of the deep well effect. The most efficient mission design uses almost no fuel while falling toward the sun, keeping nearly the entire supply for the brief engine burn at perihelion. The sun's own gravity provides the inward acceleration without costing a single drop of fuel. The spacecraft simply has to begin its descent under the correct initial conditions, and from that point, the geometry naturally guides the rest of the journey. This is one of the clearest demonstrations in space exploration of allowing gravity itself to perform most of the work while saving the engine for the one moment when its contribution matters the most. Imagine the flight unfolding step by step. The spacecraft departs from Earth and heads inward, gaining more and more speed as it falls closer to the Sunday. The heat shield begins to glow brighter. Through the window, the sun grows larger than it has ever appeared to any spacecraft that has ventured through space. At perihelion, the instant of both maximum danger and maximum opportunity, the engine ignites for only a few minutes. The burn is so short because the orbital geometry is exceptionally favorable, allowing a brief burst of thrust to reshape the spacecraft's path. Once the maneuver is complete, the spacecraft begins climbing away again, but now along a route that no direct upward launch could ever achieve. Its new trajectory lifts it out of the planetary plane, carrying it toward the sun's polar regions without requiring the enormous amount of brute force delta V that such a climb would normally demand. There is also another way to escape the plane, and this method requires no fuel at all. A solar sail is an enormous, ultra-thin reflective surface that captures the faint pressure created by sunlight itself. Every photon that strikes the sail and bounces away transfers an incredibly tiny amount of momentum to it. The force delivered by a single photon is almost impossible to imagine because it is so small. Yet when that force is spread across a sail covering thousands of square meters, and when it continues acting day after day, month after month, and year after year, the total momentum steadily builds. Over time, the sailcraft can dramatically alter its orbit without ever burning propellant. The sail-powered spacecraft can slowly spiral inward or outward, adjusting its orientation to use sunlight in much the same way a sailing ship adjusts its sails to catch the wind. By rotating the sail to different angles relative to the sun, the spacecraft can choose whether to increase its orbital energy, reduce it, or gradually tilt the entire orbital plane. These options are more restricted than those available to a chemical rocket because the direction of the available thrust is always tied to the sun's position and to how the sail is angled. Even so, within those natural limits, a solar sail can accomplish maneuvers that would be far too expensive for a conventional rocket by simply allowing the gentle push of sunlight to accumulate over long periods. Solar sails capable of carrying out meaningful interplanetary maneuvers must have surfaces covering thousands of square meters. The material used for these sails consists of remarkably thin films, only a few microns thick, with edges stretching for kilometers once fully unfolded. Before launch, the sail is packed into a compact volume, then carefully deployed in space through highly engineered deployment systems. Small experimental missions have already proven that this technology works, and modern spaceflight possesses the engineering ability needed to build it. What has not yet existed is the financial investment and political commitment necessary to construct a sailcraft large enough for major solar polar missions. For decades, scientists have studied several mission concepts that would use solar sails to explore the sun's poles. One long-standing proposal involves a solar polar imaging mission in which a sailcraft slowly spirals closer to the sun while continuously increasing its orbital inclination using nothing but sunlight pressure. Another detailed concept follows a similar high-inclination mission design. Both approaches rely on the quiet, continuous force of sunlight to accomplish what chemical propulsion cannot realistically achieve within practical delta V limits. Even after many years of study, neither mission has yet become reality. The greatest strength of a solar sail is simple. It never runs out of fuel. As long as sunlight continues shining, the sail continues generating thrust. The lifetime of such a mission depends primarily on how long the sail material and onboard electronics remain functional, rather than on carrying a limited supply of propellant. A sail-powered spacecraft traveling to the sun's poles could theoretically reach a polar orbit, spend years observing those regions, and continue adjusting its path whenever necessary without ever losing its ability to maneuver. The economic and operational advantages of fuel-free navigation are enormous. Although building a solar sail large enough for these missions requires significant development costs, the main limitation of the technology is that its thrust remains extremely small. Engineers must accept that a sail-driven journey to the sun's poles will require several more years than a mission using a perihelion engine burn. Every maneuver happens gradually. Every orbital adjustment takes time. A mission willing to patiently complete a spiral lasting many years can ultimately reach destinations that would be beyond the financial reach of any chemical propulsion mission. The trade-off is unavoidable. Fuel is saved but time becomes the price. The most promising modern mission concepts combine both approaches. A sailcraft launched from Earth first relies on sunlight pressure to spiral inward toward the sun without consuming any fuel. As the sailcraft nears perihelion, the sail is either folded away or released, allowing a compact, high-energy propulsion stage to ignite at the exact moment of closest approach to the sunday. That burn places the spacecraft on a path that rises sharply out of the planetary plane and into a polar orbit around the sunday. This combined design exchanges added engineering challenges, two different propulsion systems, two very different thermal conditions, and a carefully planned transition between them for a major reduction in the total delta V required compared with using either method by itself. In simple terms, the solar sail performs the slow, energy-efficient task of guiding the spacecraft close to the sun, while the perihelion burn delivers the short, powerful push needed to launch it out of the plane. The concept brings together the long-distance efficiency of solar sailing and the instant power of a deep solar burn. The outcome is a mission that no chemical rocket by itself could realistically achieve, and that no solar sail alone could finish within a practical amount of time. Together, the two systems become far more capable than either one on its own, just as thoughtful engineering often makes possible. Different versions of this combined approach have been examined for decades. Scientists and engineers have introduced mission ideas, improved them, simulated them, and then placed them back on the shelf many times while waiting for the right mix of scientific interest, financial support, and political circumstances to finally make one a reality. So far, none of these missions has been constructed. They remain among the many remarkable concepts in space exploration that have been fully developed on paper, partially validated through component-level testing, but never assembled into the complete spacecraft their creators originally envisioned. Other propulsion systems may also make out-of-plane missions possible, if given enough time to mature. Ion engines, which rely on electrical energy to accelerate ionized particles to extremely high exhaust velocities, are much more fuel efficient than chemical rockets when measured by the amount of delta V produced for each kilogram of propellant. These engines have already powered several deep space missions, allowing maneuvers that conventional rockets could not have carried out economically. With sufficient electrical power and enough years of operation, an ion-powered spacecraft could gradually change its orbital inclination and slowly climb out of the planetary plane without depending on a planetary gravity assist or a deep solar burn. Although each moment of thrust is very small, it never stops. And over many years, that steady acceleration can create an enormous overall change in velocity. Nuclear electric propulsion offers an even more capable possibility for traveling out of the plane. In this concept, a compact nuclear power source supplies electricity to highly efficient electric thrusters. Because a nuclear reactor can generate far more power than solar panels, especially in regions where sunlight becomes weak, such a spacecraft could accomplish far more ambitious missions. Given enough power and enough time, a nuclear electric spacecraft could slowly move above one of the sun's poles, remain there for years making continuous observations, and adjust its position throughout the mission as needed. Engineers have examined this technology in considerable detail, although it has not yet been flown on the scale required for a mission of this kind. When a solar polar mission is eventually approved, choosing between these different mission designs will depend on many factors, including cost, schedule, scientific goals, and political priorities. The purpose of this part tonight is not to argue that one solution is better than another. The goal is simply to show that these missions are achievable. The layout of the solar system is not an impossible obstacle. The wall of delta V can be overcome through smart use of gravity, sunlight, carefully timed burns close to the sun, and the slow, continuous acceleration that ion engines and solar sails can provide. The sun's polar regions are not forever out of humanity's reach. They remain unexplored only because they lie beyond the types of missions we have chosen to build until now. The central idea of this section is that sometimes a spacecraft must first fall before it can climb. It is a quiet reminder that the universe often rewards those who work alongside gravity instead of trying to defeat it. The same force that flattened the early protoplanetary disk keeps the planets following their familiar paths and locks every spacecraft into the sideways motion of the ecliptic, also provides the very route needed to escape that motion, provided there is enough patience to reach the right place before applying the necessary push. The sun's deep gravitational well is not merely an obstacle standing in the way. It is also the tool that makes the journey possible, used at exactly the right time, in the proper direction, and after careful preparation, the sun's own gravity can place a spacecraft at a viewpoint that no direct upward climb could ever achieve. Imagine, for the remainder of tonight's final part, that such a mission has finally become reality. Imagine that the mission architecture has been selected, the spacecraft has been completed, the planned trajectory has been successfully flown, and the spacecraft has at last arrived above the sun's north pole or below its south pole, maintaining a comfortable distance in a slow and steady orbit that allows uninterrupted observation. Every scientific instrument is operating normally. The communication link remains stable. The mission is now underway. What would the spacecraft experience? The first thing that changes is the appearance of the sky itself. From within the ecliptic plane, the night sky is softly brightened by the zodiacal light, which is created as sunlight is scattered by countless tiny dust particles, concentrated along the plane where the planets orbit. This glow is subtle, yet it stretches across the entire ecliptic and limits how faint the stars and distant galaxies can appear to an observer located within that plane. Once the spacecraft rises above the ecliptic, that glow remains beneath and behind it, instead of spreading light into its upward view. The sky above becomes darker and cleaner than any view that can be obtained from inside the planetary plane of the solar system. Faraway stars, dim galaxies, the cosmic microwave background, and the ancient imprint left by the early universe would all stand out against a much darker and less contaminated background. The scientific value of observing the universe from such a location would be enormous. Telescopes designed to search for biosignatures in the atmospheres of distant exoplanets are restricted both on Earth and in low Earth orbit because of scattered light produced by the zodiacal dust cloud. That glowing dust creates a permanent foreground that competes with the extremely faint signals coming from the atmospheres of distant planets. A telescope positioned above the solar system's plane would observe through one of the clearest viewing windows available anywhere in the inner solar system, where zodiacal contamination would be greatly reduced. As a result, the weakest signals arriving from remote worlds would be much easier to separate from the darker background. Observations of the cosmic microwave background, the faint leftover radiation from the universe's earliest moments, are affected in much the same way by light emitted from dust within our own solar system. A viewpoint above the ecliptic would greatly reduce that interference, making it possible to produce more accurate maps of the tiny temperature variations within the microwave background. Those slight temperature differences preserve valuable information about the state of the universe shortly after its beginning, and the accuracy with which astronomers can measure them determines how precisely they can rebuild the story of cosmic history. A darker and cleaner sky improves this effort and strengthens nearly every branch of cosmological observation. Even more traditional forms of astronomy would see important improvements. Studies of variable stars, pulsar timing experiments, and long-term monitoring of extremely faint objects would all benefit from a sky with far less scattered light and fewer foreground distractions. Time domain astronomy, which relies on detecting very small changes in the brightness of distant objects over long periods, would become more sensitive thanks to the darker observing conditions. Looking down from above the planetary plane is valuable not only for studying the Sunday, it also provides one of the cleanest possible locations for exploring the rest of the universe. The environment immediately surrounding the spacecraft would change as well, while it continued its climb away from the ecliptic. Near the solar equator, a spacecraft travels through the slow, turbulent, and constantly changing solar wind associated with the streamer belt. There, slower moving plasma rises from the edges of equatorial structures that are threaded by the rippling current sheet, with both density and direction changing from hour to hour. As the spacecraft reaches higher solar latitudes, the surrounding solar wind gradually becomes different. The plasma begins flowing faster, becomes steadier, and grows much more uniform as the spacecraft enters the fast solar wind streaming directly outward from the polar coronal holes, where the turbulence and variability, typical of equatorial regions, are much weaker. This transformation does not happen all at once. It unfolds gradually across a broad range of latitudes as the spacecraft leaves the streamer belt behind and enters the polar wind region. Between these two wind systems lie complex transition zones containing mixed plasma, where fast streams overtake slower ones and create compression fronts along with stream interaction regions. Earlier polar missions mapped these high-latitude transition regions only at relatively low resolution, yet they uncovered structures far more complicated than the simplest theoretical models had predicted. A long-lasting polar mission would be able to examine these transition regions with much greater detail. The energetic particle environment would also evolve during the journey. Cosmic rays, which are partially redirected by the heliosphere's magnetic field while traveling inward from interstellar space, would reach the spacecraft with slightly different energies and arrival rates depending on its solar latitude. The flow of galactic cosmic rays is especially valuable to study at high latitudes because the shape of the heliosphere's magnetic field changes with latitude, influencing how easily those particles can enter the inner solar system. A spacecraft operating above the ecliptic for many years while continuously measuring cosmic rays would help scientists better understand how the heliosphere regulates the galactic cosmic ray background. Measurements of the magnetic field at these high latitudes would also provide a direct test of the surprisingly uniform, large-scale magnetic structure that earlier observations had hinted might exist. As mentioned earlier, once you move beyond the Sun's immediate polar regions, the radial part of the heliospheric magnetic field becomes nearly identical in every direction. This happens because the outward flow of the solar wind gradually smooths the magnetic flux as it spreads through space. A dedicated polar mission that measures the magnetic field continuously over many years could reveal exactly how this remarkable uniformity develops and how it changes throughout the solar cycle. The structure of this magnetic field remains one of the most fascinating questions in heliospheric science, and observing it from above the Sun's poles provides the ideal viewpoint. If the spacecraft then aimed its instruments back toward the planetary plane, it would achieve another historic milestone. Humanity would, for the very first time, see the solar system's disk from directly above. The planetary orbits, which are normally reconstructed from observations made within the same plane, could instead be viewed all at once. The dust bands of the inner solar system, the asteroid belt, and the paths travelled by comets would all appear together as one enormous flattened layer beneath the spacecraft, illuminated by the sun from behind. For the first time, The true layout of our cosmic neighborhood would be visible from a position that reveals the complete design in a single view. Earth and the other inner planets would appear as tiny bright points moving gradually along their orbital paths. The entire inner solar system would fit inside one field of view. The location of every planet, the distances separating their orbits, their relative motion, and the slight orbital inclinations that make each path unique would all become visible in a way that cannot be achieved from anywhere inside the planetary plane. The resulting image would become the first true overhead portrait of the inner solar system, captured as one complete object. The asteroid belt would appear as a faint ring, extending slightly above and below the main plane in certain regions, while remaining largely concentrated between the orbits of Mars and Jupiter. The overall distribution of asteroids, the empty gaps created through orbital resonances with Jupiter, and the large Trojan asteroid groups sharing Jupiter's orbit would all be immediately recognizable from this elevated perspective. Dust released by short period comets together with material originating from Kuiper Belt, objects would stand out much more clearly against the darker background outside the planetary disk, allowing scientists to separate the different dust sources with far greater accuracy than is possible from within the disk itself. This image would represent the first true overhead portrait of the entire solar system viewed as one complete object. No such picture exists today. Humanity has never captured it. It cannot be photographed from anywhere inside the planetary plane because the geometry itself makes such a view impossible. Only a position well above or below the disk can reveal the full arrangement of the system. Until now, no spacecraft has remained in such a location long enough to produce that image. A complete portrait of our solar system as a thin, flattened structure seen from above remains one of astronomy's greatest missing pictures. With a mission lasting many years and enough travel outside the planetary plane, the spacecraft could also settle one of the biggest unanswered questions about the heliosphere itself, its true shape. Direct observations of magnetic fields and plasma at high solar latitudes, collected across different distances from the Sun, would allow scientists to distinguish between the traditional comet-shaped model and the alternative deflated croissant model. These competing ideas predict different boundary shapes, different magnetic structures at high latitudes, and different arrangements in the region extending behind the Sun's motion through interstellar space. As the spacecraft gradually moved outward along its highly inclined orbit, it would pass through regions where the predictions of these two models no longer agree. If it eventually crossed the heliosphere's outer boundary from above or below, regardless of how far from the upwind nose that crossing occurred, it would return the first direct measurements ever collected beyond the planetary disk. Such an achievement would play the same role for heliospheric geometry that previous boundary crossings within the planetary plane played for the upwind direction. It would expand our in-place map of the heliosphere into regions that have never before been explored. No matter which model proves correct, the results would dramatically improve our understanding of the enormous bubble surrounding our solar system. If the comet-shaped model is confirmed, scientists would better understand how the Sun's magnetic field controls the long downwind structure of the heliosphere, and how its interaction with the surrounding interstellar magnetic field either supports or prevents the formation of an extended tail. If the deflated croissant model turns out to be correct instead, the familiar textbook picture would need to be completely revised. It would suggest that the heliosphere is much more compact than previously believed, with its boundary lying closer to the Sun in every direction, and magnetic pressure playing a far more important role than earlier models proposed. Whichever picture proves to be true, humanity would finally possess a clear outline of its cosmic home based on direct observation. instead of careful inference. Looking even farther beyond the heliosphere, the appearance of the Milky Way itself begins to change when viewed from this remarkable polar perspective. The plane of the Milky Way, inclined by about 60 degrees compared with the ecliptic, would no longer stretch across the sky in the familiar pattern we see from Earth. Instead, it would appear as a broad, tilted ribbon with the brilliant bulge at the center of the galaxy positioned in a completely different part of the sky than it appears from within the shared plane of the planets. The constellations that belong to Earth's southern sky, the dark rivers of dust winding through the Milky Way, and the gentle glow of the galaxy itself would all be arranged in a geometry very different from the one we have always known. Looking south, beneath the sun's south pole, opens one of the clearest viewing paths through the local bubble, the vast, low-density region of interstellar space surrounding our sun that was carved out by ancient supernovae. From this direction, the universe appears just a little deeper, the nearby gas becomes slightly thinner, and the dust that blocks distant objects is a little less concentrated. A telescope aimed from below the sun toward this region would enjoy a remarkably clean window into the wider Milky Way, with much less interference from nearby interstellar material than observations made from within the planetary plane. The shape of the local bubble, the much larger cavity through which the sun is currently drifting, has a structure of its own. It is not a perfect sphere. Instead, it forms an elongated hollow created by explosions of nearby massive stars during the past several tens of millions of years, with chimney-like openings extending vertically above and below the galactic disk, while the structure within the disk itself is far more complex. Observing from a polar position toward the galactic poles would reveal parts of this bubble that are extremely difficult to examine clearly from inside the plane. Even the cosmic microwave background, the faint leftover radiation that fills the entire universe and preserves information about conditions when the first hydrogen atoms formed, could be measured from an unusually clean location. Although this ancient radiation exists in every direction, emissions from both the Milky Way and our own solar system make highly precise measurements more difficult when observing from within the disk. A polar viewpoint would greatly reduce the unwanted signals coming from the solar system, leaving behind a cleaner remaining background. Its tiny temperature differences, its patterns of polarization, and the subtle marks left by the first structures that emerged in the early universe could all be studied with greater precision. Even ordinary stars viewed from above the planetary plane would stand out against a darker sky than the one available from Earth. Dim stellar companions, faint exoplanets reflecting the light of their parent stars, and barely visible brown dwarfs drifting around the edges of stellar systems would all become slightly easier to detect because they would appear against a less cluttered background. In many ways, a polar viewpoint offers a modest but meaningful improvement for nearly every branch of astronomy that relies on finding extremely faint objects hidden within unwanted background light. There is still no photograph of the solar system taken from outside its own plane. There is still no high-resolution image of the sun captured directly above one of its poles under calm conditions and maintained long enough to watch its changing behavior in real time. Those pictures simply do not exist yet. They are not beyond our reach. The engineering is available. The underlying principles have been understood for a long time. The flight paths have already been calculated. Mission designs have already been developed. The only thing missing is that no one has actually launched such a mission. The region above the sun remains one of the most valuable observation points anywhere in the solar system. Even today, it remains empty, waiting for a spacecraft that has yet to be built. Every direction from which humanity has ever observed our solar system has remained within the disk itself. Our solar system is fundamentally flat, and throughout the entire history of astronomy, we have continued studying it from inside that same flat structure. The sun's poles, the upper and lower regions of the heliosphere, and the vertical axis of the disk all lie within an area that has only been briefly visited by 2 spacecraft, neither of which could do much more than collect a limited sample of what exists there. A complete view from above has still never been added to our records. It remains one of the last major blank spaces in our local map. It can be completed. It simply is not being completed yet. The sun has already waited 4.5 billion years for its first long-lasting view from above. It can wait a little longer. The mission is entirely possible. The engineering already exists. The trajectories have already been worked out. What continues to be missing is the financial support, the political commitment, and the patient agreement among the people responsible for planning these missions that this unique viewpoint deserves the investment. The viewpoint deserves that investment. Tonight has been about understanding exactly why the geometry of our solar system, the nature of our nearest star, the shape of the bubbles surrounding us, the appearance of the planetary disk when seen from above, and the orientation of the Milky Way from beyond that plane all depend on the one perspective humanity has never captured. The flat shape of our solar system has influenced every picture of the heavens humanity has ever captured. It has guided the path of every spacecraft ever launched. It has determined the orbital mechanics behind every mission, the arrangement behind every observation, and the boundaries of what every telescope is able to detect. This flat plane is not an accident. It is not something standing in our way. It is simply the natural result of the way a young solar system formed and preserved its structure over time. Humanity has spent its entire existence inside that structure, and we will remain within it for a very long time. The only real question, the one that has quietly stayed with us throughout tonight's journey, is when we will finally decide to observe it from a place beyond that familiar plane. The sun continues its slow rotation, just as it always has, resting calmly at the center of the disk. The planets keep circling it, just as they always have. The fast solar wind still rushes outward from the poles, just as it always has. The current sheet continues to wave through space, just as it always has. The heliosphere maintains its form, whatever that true form may be, while pressing against the surrounding gas between the stars. Every one of these processes continues, has always continued, and will continue whether anyone is there to witness them from the directions that would finally reveal the complete picture. None of these natural processes depends on a photograph. That photograph exists for us alone. And so the quiet thought of the view we still do not have becomes the gentle idea connecting everything we have explored tonight. The plane remains flat. The poles remain unseen. The great bubble surrounding our solar system remains only partly mapped. The family portrait of our cosmic home is still incomplete. We already possess the engineering. What we have not yet fully gathered is the determination to make the journey. All of these statements are true together, and none of them demands immediate action tonight. The universe is patient. The sun is patient. This great disk has kept its shape for 2 billion years, and it will continue to do so for billions more. The view from above will arrive when the time finally comes, and that long-awaited image will become part of our record when it is finally captured. Until that day, the structure remains in place. The flight paths remain unwritten. The spacecraft capable of making that journey still wait for their moment. None of this asks anything from the person listening. So we allow the sun to remain where it has always been, slowly turning at the peaceful center of the disk that has carried us for 412 billion years. The space above its poles remains empty for now. The missing photograph is not something we have lost. It is a promise quietly waiting for the paths through space that humanity has not yet traveled. The flatness surrounding us remains unchanged. The planets continue their calm journeys. The solar wind continues its endless outward flow. None of these things asks anything of us tonight. Let your breathing become slower. Let the quiet, wide plain of our planetary neighborhood gently settle around you. Let the space above and below the sun remain silent, just as it has always been.